So this is the fourth and final lecture of the anomalous Zeeman effect. So remember, we had just calculated the correction due to the relativistic kinetic energy, at least the first order term right here, and we got out to be this, and then we said that was on the same order of magnitude as the spin-orbital coupling due to the magnetic field due to the spinning proton around the electron. So if I wanted to get the total correction, all I need to do is just add these two effects up. And so if we were to just add those up, we would get delta E total. We can keep our E sub n alpha squared, E sub n alpha squared all over n squared factored out. And then maybe I'll put this term first minus that term, n over n all over L plus a half minus 3/4 plus n times 3/4 plus L times L plus 1 minus J times J plus 1 all over 2L times L plus a half times L plus 1. So there would be the total change. We should be able to simplify this. What I'm going to do is, just so I don't have to carry everything around, I'm just going to try to simplify this and these two put together, because that's pretty much already simplified. It's just minus 3/4. Okay. So I'm just going to pull out the 2 in the circle right there. Well, there's a constant, there's an n that I can pull out, so this is just the total encircled right here. Let me write it like this. Okay, so we got an n, and then we've got we've got 1 all over L plus a half plus, and then we pulled out that n, so it's just 3/4 plus L times L plus 1 minus J times J plus 1 all over 2L L plus 1/2 L plus 1. So that's just the 2 in the red circle right there. Okay, I just want to get a common denominator here. If I get a common denominator, I already have an L plus a half here. So it looks like what I need here is I need a 2L times L plus 1. And the same in the bottom. 2L times L plus 1. Okay, so this gives me n. And then we have the denominator is all a constant, right? That's all, they're both the same. It's 2L times L plus 1 times L plus a half. Okay, and then in the numerator, if I were to multiply this thing out, the first term would be 2L squared. And then we got plus 2L. And then we got plus 3/4. And then plus L squared. And then plus L. And then minus J squared. And then minus J. Okay. Now, this is, again, n. Now, 2L squared plus L squared gives me 3L squared. 2L plus L gives me 3L plus 3/4 minus J squared. Remember, the definition of J is L plus or minus a half, right there. So if J is equal to L plus or minus 1/2, then J squared is equal to L plus or minus 1/2 times L plus or minus 1/2, which is equal to L squared. And then the last term, this and this right here, it's either the two pluses, which would give you 1/4, or the two minuses, which would give you 1/4. So they're both cases, they're 1/4 plus. Okay, and then if we were to pick the two top cases, we'd have L plus, when we do the cross multiply, it would be a half L plus a half L, that's plus L, or if you had the plus, it would be the plus L. If you had the minuses right there, you'd have minus L and another half of minus L, which would be minus L. So it should just be this right here, which is, I just wanted to, it's plus minus L. Okay, so there's what J squared is right there. So I'm going to put that in. So this was minus J squared, so it's minus L squared minus 1/4, since we have a minus there, minus 1/4, and then it's a minus plus minus, which would make it a minus plus L. Remember, the top one is for the J plus a half and L plus a half, and the bottom one would have been for the L minus a half. Okay, so that's this right here, and then we got minus J. Well, minus J would just be minus L, and then multiplying that by minus is minus plus 1/2. Okay, so that takes care of that. All over 2L times L plus 1 times L plus 1/2. Okay, now we can simplify this more. We get an N squared. We got a 3L squared minus L squared. That's 2L squared. And then we get a 3L minus an L, which gives me a 2L. I better not put that one in yet. So you got a plus 2L. Okay, we've got a 3/4 minus a 1/4. That's 1/2 plus 1/2. Okay, and the only two terms we've got left is this one and that one. So we got minus plus L. And we also have minus plus a half. And we still have on the denominator still the same thing. 2L, L plus 1, 2L times L plus 1 times L plus a half. Okay, so now, for the top case, if we're going to take the top case, that was the top case up here. So for the top case, for the plus and minus top case, that's when J is equal to L plus a half. J is equal to L plus a half. And if for that case, we would use the top plus and minuses right there. So that way, this whole thing becomes N squared, 2L squared, plus 2L plus a half. And now we're taking the top sign, top case, minus L minus a half. Minus L minus a half. Okay, and so all over 2L, L plus a 1, L plus a half. Okay, now we get a 2L minus L, the halves dropped out, and we get n squared and 2L squared. Oh, this is just plus L. This is just 2L squared plus L, 2L squared plus L, all over 2L, L plus 1, L plus 1 half. Now, if I pull a 2L out of here, if I pull the 2L out, this is n squared 2L, and we're left with an L plus a half. All over 2L, L plus 1, L plus 1 half. Well, the L plus 1 halves drop, the 2L's drop, and so this just becomes n squared all over L plus 1. So these two terms, remember that's what we're looking at, these two terms for the case when J is L plus a half, that whole thing just knocks down to n squared over L plus 1. Now if we look at the bottom case, that means we're using the two pluses down here. So we got n squared, 2L squared plus 2L, 2L squared plus 2L, plus a half. Now we're using the bottom one, so it's plus L plus a half. Plus L plus a half all over the bottom. 2L, L plus 1, L plus a half. Okay, and then we can simplify this. The 1 half gives me a 1. So this would be 2L squared. Okay, so this is n squared. And we got 2L squared plus 2L. 2L squared plus 2L plus L plus 1. Plus L plus 1. All over 2L, L plus 1, L plus a half. 2L, L plus 1, L plus a half. Now, I can factor out of these two terms, I can factor out a 2L, and that would just be left with L plus 1. And then over here, I also have another L plus 1. So I can factor out the L plus 1 out of those two terms, and so this is n squared, we're factoring out the L plus 1. And so we're left with 2L plus 1 all over 2L times L plus 1 times L plus 1 half. Okay, well, the L plus 1's drop out. And if I multiply this 2L, sorry, if I multiply the 2 through, 2 times all of that will just give me 2L plus 1. So that cancels with this and this right here. And so this thing just becomes n squared over L. So it's n squared over L. So this is when J is equal to L plus a half. And this is the case where J equals L minus a half. So now let's just plug this thing back in. That would be what these two terms are put together. So we have E sub n alpha squared. So we got delta E total is equal to E sub n alpha squared all over n squared. And then we have put the minus 3/4 in there first. So we got that minus 3/4. And then we get either this or that. We got plus either one of these depending on which one J is. So you got plus, maybe I'll write it like this. I'll write it like it's n squared all over L plus 1. So this is what it is when J is equal to L plus a half, and it's n squared over L when J is equal to L minus a half. You would use that, and when J is equal to L plus a half, you'd use the top one. But I think we can simplify this further because, you know, if for the top case, if J is equal to L plus a half, right there, then what's L? L right here. Oh, actually, yeah, what is L? L is equal to J minus a half. Right here. And what is L plus 1? Well, L plus 1 is just this plus 1. That's just J plus a half. So I could replace L plus 1 with J plus a half. But before I do that, let me look at the bottom case. You notice right here, if if J is equal to L minus a half, if J is equal to L minus a half, then L is equal to J plus a half. J plus a half. So I could replace this L with just J plus a half, and I could replace this L plus 1 up here with J plus a half. So they're both the same, so I don't have to write them down as two different things. They're both just J plus a half in the denominator right here. So it looks like delta E total is equal to E sub n alpha squared all over n squared. We got the minus 3/4. Maybe I'll put this term first. We get n squared all over, we said both of these two terms was J plus a half minus 3/4. Okay, so that right there we call the fine structure. Fine structure right there. So what does that do? That right here, what's that going to do to the energy levels? Remember our energy levels. We had, I'll write it over here. We had our n equal 1. We'll just look at the 2. N equal 2 state. N equals 2 state right here. We know what the L is here. L is equal to 0. And what do we say? When L is equal to 0, J what do we say? J can only be a half. J can only be a half. J equals 1/2. And so when we write it in spectroscopic notation, remember we use this notation right here, NL sub J. So this, we would have called this the 1s 1/2 state right here. Well, you notice it doesn't, well, now if we come up to here and see how much the energy shifted by, the delta E for the 1s 1/2 would be E sub n alpha squared all over, well, n is 1, so I don't have to put any 1 right there, so just be that, times n, which is 1. 1 squared is still 1. That was, sorry, why did I say n? N squared is 1. N, actually, see this n right here? It was just n right here. It was just n. It's just n all the way through. We never brought any more. They're all just n's right here. So there's no n squared. So this was just n and an n right there and an n right there. Okay. So this would be 1 all over J. J was a half. A half plus 1 is 1 minus 3/4. Okay, and E sub n, we do know what E sub n is. It's minus 13.6 for the first level right there. Minus 13.6 EVs times 1 over 137 squared times 1 minus 3/4, which is 1/4. So what is this thing going to do? It shifts it down a little bit because it's a minus, and it's going to shift it down, not very much right here, because this is like, 1/50,000th of this right here. So it's just going to slowly lower it a little bit right here. I'm exaggerating quite a bit. So this is without the fine structure, and this is with the fine structure. This would be the 1s 1/2 state right here. It would lower it a little bit in energy. Well, up here, what do we have? We have L can be 0 or L can be 1. If L is 0, then J is a half. J equals 1/2. And we would call this the 2s 1/2 state. 2s 1/2 state. If L is equal to 1, then J can be plus, remember J can be L plus or minus a half, so J can be 1/2 or 3/2. And so this would give me, one of them would give me the 2p 1/2 and 2p 3/2. So the 2p 1/2 and 2p 3/2. Now, we would have said they were all the same energy before the fine structure. They would have all been right on top of each other, but the fine structure is going to shift some more than others. Well, it looks like it only depends on J and N. And so it looks like these two states are going to both separate the same amount because there's no L over here, and that's the only one that separated those out. So let's look at like the 2s 1/2. So for delta E for the 2s 1/2, if we plug it in, we would get N is 2, so that would be minus 13.6 over N squared, which is 4. But you also have another N squared there, so you got another 4. We got our alpha squared, 1 over 137 squared, times N, which is 2, all over J, if J is a half, So a half plus a half is 1, so it's 2 over 1 minus 3/4. Okay, and so this is 8/4 minus 3/4 is 5/4. So this is 5/4. So this is minus 13.6 over 16 times that alpha squared, 1 over 137 squared times 5/4. Okay, again, it's bringing it down right here. And it looks like, does it bring it down more than the other one? The other one, just comparing these two, this one, after you figure out they both have a 13.6 and they both have 137 squared, this one has a 1/4. This one has a 5 over 64th right here. So it looks like this one came down more. This one up here is going to come down a little less right here. So we've got this one coming down. This would have been we would have called that the 2s 1/2. It's going to be the same as the 2p 1/2 because the only difference is L and there's no L in there. So this is the 2s 1/2 and the 2p 1/2. 2s 1/2 and the 2p 1/2. Okay. Now if we look at the other state, we also had the 2p 3/2. So the delta E for the 2p 3/2. Well, let me see. This one right here, it's still n is 2, so it's minus 13.6 over 4, 2 squared. We still have the 2 squared there, so we have the other 4. We have the 137 squared, 1 over 137 squared. N is 2. J now is 3/2 plus 1/2 is 2. So 2 over 2 is just 1 minus 3/4, which is just 1/4. Up here it was 2 minus 3/4. This is only 1 minus 3/4. So this is a smaller amount. It drops by a smaller amount. So this one is going to come over to here, and it's going to be right there. And this one is 2p 3/2. So it separates out for the different j values. So we would have started to see this right here. Now, again, this isn't the end of the story right here. Seems like it's never the end of the story because there is, I still haven't brought up what is the anomalous Zeeman effect. This is the fine structure. But what happens, remember the Zeeman effect is what happens when you put it in a magnetic field. Well, when we put it in a strong magnetic field, this coupling is destroyed and you're back to this, and we're back to our old normal Zeeman effect. But what happens if the magnetic field isn't strong enough, the external magnetic field isn't strong enough to decouple this? Well, then that means that we would also have to take into account, now we're talking about a weaker magnetic field. It doesn't have to be too weak. The field due to the orbiting proton is quite strong, but all we would have to do is we would have to just correct. Now, remember, what did we say when we had the magnetic field in there? The correction was EB all over 2m. That was times, our correction, EB all over 2m, J sub z plus S sub z. Now, I'm not going to work all this thing out. We would have to do the psi with the x and put that inside of it, but I'm just going to tell you right here what that does when you put this into a weak magnetic field. It's going to give you an energy shift for the case when J is equal to L plus a half. It's going to shift it by, remember, It's going to shift it by mu BB. B is this external magnetic field that you're putting it in, times 2L plus 2 all over 2L plus 1. That's what you'd get, right, after a lot of work right here. And for the other case, the delta E for the J equal L minus a half, that would be mu BB times 2L all over 2L plus 1. Okay, so now, what would that, let me move this over 2S1 half, just so I can, 2S1 half, just so I can see what's going to happen now to these states right here. Now, to this state right here, this 2S plus, this is the energy shift between the M sub J's right here. And so, remember, we have M sub J here. Since J is equal to 1 half, M sub J is minus 1 half and 1 half. And so this is going to tell me how much it's going to, the splitting between these two lines. These two are going to split. This is the splitting right here. Now, since we're in the case where J is 1 half, that's equal to L plus a half, which is that L is 0. So we're looking at, this is the spacing between them, since we're looking at the L plus a half. And so this spacing right here, you would just plug in what L is. Well, what's L for the S state? L is 0. So that would just be 2 over 1. It'd be 2 mu BB. 2 mu B. That's how much they would separate for. Now, this one, this one up here is the, which is, I'm just going to look at the 2S1 half, this one right here. I'm not going to look at this one. We'll just look at this one right here. So I'm going to bring this one back a little bit, so I'm not going to care about him. But if we look at this one right here, we get the 2S1 half. Well, this is the case right here where J is equal to L plus a half, because L was 0, and so that's why you got that one. And so if we come along here, and we're going to use this case right here, and for this case right here, L is 0, and so if L is 0, that just becomes 2 mu BB. So this case, this one right there is going to separate these out by 2 mu BB. And then I just want to look at this other one, this 2p1 half state. Well, this p1 half state, we know L is equal to 1, and so this must be the J equal L minus a half case, because J is a half and L is 1. So we're going to use this case down here, and for the L equal to 1 case, that just becomes 2/3 mu BB. So this one right here is going to separate out only into 2/3 of mu BB. So it's going to be a little bit smaller. So this spacing right here is 2/3 mu BB. Well, that means if this is 2/3 mu BB, this is 1/3 mu BB. And if that's 1/3 mu BB, that means that this is also 2/3 mu BB. So it looks like these are 4 equally spaced lines, and they're all equally spaced by 2/3 mu BB. So really, it looks like this and this and this. They're all equally spaced right here. Now this one right here would be the anomalous. These guys were separated by 2 mu BB. These are by 2/3 mu BB, and so on. They have different spacings right here. Remember, with the normal Zeeman effect, all the spacings were the same. Now they're different. And then this one's going to have some different spacings right here, and so on. Now, it's still not the end of the story right here. This story just keeps going on right here. I just wanted to say one other thing, and that is we haven't taken into account there's actually another device in there, because the proton also spins right here, which means he has a magnetic dipole moment too, mu of the proton right here. And that's going to be G, remember the G of the proton, E all over 2 mass of the proton times the spin of the proton right there. So, right there. So you've also got another magnet in there. Now, this is mass of the proton. The other one had the mass of the electron down there. Well, this, the mass of the proton is 2,000 times bigger. So this is already a factor of 2,000 times smaller right here. And we might say, what is G sub P right here? We said G of orbiting electron was 1. The spinning electron is 2. It's just that this is 5.59. It's probably because the proton is a complicated structure. It's got quarks in it and stuff. And now you've got 3 magnets. You got the orbital, you got the 2 spins right there. But if you look at the L equals 0 case, then we can forget about one of them right here and just look at the 2 spins right here. So if you look at the L equals 0 line, then the change in energy is just due to the coupling between the 2 spins. And what you're going to get, if you work this thing out right here, without the magnetic field, let's take back out the magnetic field, what you're going to get is you're going to get some splitting right here, again due to the spinning proton. And this splitting of this low state, this L equals 0 state right here, turns out to be 8/3 G of the proton, that 5.59, times the mass of the electron over the mass of the proton, which is our factor of 1 over thousands right here, alpha squared times your E sub n. In this case, it's E sub 1 because we're looking at the n equal 1 level right here. Now, this line, this width right here is, in terms of EV, is 5.8 times 10 to the minus 6 EV. Remember, this level is at minus 13 EV. And now this little split, due to the spinning proton, is 1/1,000,000th of that size right here. That's the energy, and if you turn it into wavelength, because we do know that E equals HF or HC over the wavelength, this wavelength is actually 21.1 centimeters. It's a very famous line. What's happening between these 2 states? These are the spin of the proton, spin of the electron. In one case, the proton and the electron are spinning in opposite directions, and in the other case, they're spinning in the same direction, right here. I assume that this one over here is this state, this one over here is this state right here. So if you kick hydrogen just a little bit, this is going to be the lowest state, you can make the electron and proton spin in the same direction. But this is a slightly higher energy, and this can actually drop back down right here and give off energy of this wavelength right here. It's 21 centimeter right here. It's very important astronomically because most of the matter in the universe is hydrogen, and most of the hydrogen in the arms of the galaxy is just really cool, probably down here near this ground state right here. And when it gets just slightly disturbed, it rings at exactly this frequency, 21.1 centimeters right here. So if you're looking for neutral, cool hydrogen, you set your radio telescope to this wavelength right here, and the whole universe is going to be ringing loud because of this because of this transition right here. Even though the time it takes to drop down might be 1,000,000 years to drop from here to here, it's got a long half-life, there's just so much hydrogen out there that it's ringing all over the place right here. And again, this is how in the 1950s, using this wavelength, a lot of radio astronomers spend their entire careers on this wavelength, they mapped out the galactic structure of the Milky Way right here. So you know, so it's, you notice it was all just quantum mechanics so far that dug into the hydrogen atom this far with the normal Bohr model, with the fine structure. This part over here was called the hyperfine structure. We had the anomalous Zeeman effect, and so it all comes out just from this quantum mechanics, and that's how we figure out what's going on in hydrogen. Okay.